Did I? I thought I hit screen recording.
Oh, you did.
Did I?
I thought that. I didn't know that.
It does. You can set it to include audio, so it should. Okay. It's the same thing I've been hitting, so we should be okay. I think. I've got to get back on this so I can get my little pin up. Okay. All right, so the only important part starts from there to there. All right, so what do we know in that problem? Wait. Okay, we know the volume and molarity of the H2SO4, which we know we can get to moles from that. So we can keep that in mind. What else do we know? We have a volume, of the NaOH. And this is of the NaOH. And what are we looking for? The molarity of the NaOH. All right, so when we're neutralizing it, that means it reacted, right? So what's the reaction? It's a stoichiometry problem. This is exactly like the last problem. It just looks more complicated. It does, but it's exactly the same problem as the last one. You're just not going to grams, you're going to molarity. It's the same thing. So H2SO4 plus NaOH is going to make H2O and Na. Let's go ahead and assume it does both. There's plenty of NaOH to neutralize it all. So Na2SO4, because if it says is required to neutralize, that's going to be all of it. All right, so Na2SO4, and if we balance, we need a 2 here and 2 here. Okay, all right, so we know that from this, we can get to moles of H2SO4, and if we can get to moles of H2SO4, we can use the balanced equation to get to moles of NaOH, right? And if I know the moles and I know the liters, I can find the molarity. Right? Okay. So do you like still setting it up in that algebra for molarity? For those of you that are struggling with the math, is that the easiest way for you? Okay, so molarity is moles over liters. So we'll just put the H2SO4 in it. So 0.5 equals X over 0.0457. Somebody's going to have to do math for me. So X is how many moles? 0.023. Moles of what? H2SO4. Okay, so now we can do stoichiometry. So 0.023 moles of H2SO4 for every 1 mole of H2SO4. We have to react 2 moles of NaOH. And so because you like the algebra, we'll stop there. So that times 2 must be 0.046. Is that true? So moles of NaOH. But now I need molarity of NaOH. So molarity equals moles over liters. So 0.046 moles over, they told us it took 20 milliliters. So 0.02 liters, what? Okay. I thought you caught a mistake. All right, so then when I divide that, 2.3 molar NaOH. No. No. Yes, you absolutely can show your work all in one line. The ones that are still struggling, what I'm finding is the ones that are struggling with the molarity seem to like the algebra better, but you absolutely can do that problem all in one line. You can, you would do start with the volume, so 0.04, was it 57? Yeah. Liters times the molarity, which was 0.5. And when you use the molarity in the dimensional analysis, I write it as moles over liters so I can see my stuff cancel. So this is moles of H2SO4, and then I can do for every 1 mole of H2SO4, I use up 2 moles of NaOH, and then I just know to divide that by the liters because that's going to give me moles. I mean, you can just stick it in that way, or you can solve for moles and then divide it by the liters at the end. But that way you see your stuff cancel. But that doesn't cancel. We don't want that to cancel. So you can multiply across the top. Yeah, you can do it all in one step if you want. But if this confuses you, then don't do it that way. Just use the algebra. It work. I mean, both ways work every time. It's fine. So there you go. Okay, good on those. All right, let's look at another one. What's the molarity of HCl solution if 27.3 milliliters neutralizes that many milliliters of that molar? It's the same problem, is it not? You see how all three of these are exactly the same now? Okay, do we need to do this one? Yeah, try to do that one on your own then. Let me see how many more examples I have for you. Uh-huh. But the you because it said required to neutralize, I would you got to assume all the H's. Well, you have a fixed amount of NaOH, but you could use as much sulfuric acid as it took. So if it would have only done half, you see what I'm saying? You would have only put in half. So, yeah, no. And typically the AP test will say completely neutralized, and then that way there's no ambiguity. And when it says completely, it's both H's. So, if it only yeah, but in a titration, it's not going to partially neutralize. It's going to do it all. You're not gonna know you're at the end of the titration if it doesn't do it all. So, you just don't know enough about all the acids and bases to do that. So you're fine. Did you get an answer? You think? That's what I got. Is that what you got?
Okay, wait. So I remember some problem where like you said like not to go to all 4 places or something on my paper. So I just went to like 3 sig figs and got like 0.15. Is that
Probably, but how did you go? Because I only went, this is only in 2 sig figs, and that's only in 3. Don't count decimal places.
yeah, true.
Yeah, don't do decimal places. Make sure you're doing sig figs. Honestly, it's in 3 up here. Your answer, I should have carried 3 at least through all the way through. The answer should be in 3. And I don't really, you should carry everything through and then round at the end so you don't have that rounding error at every step. But because I'm going to see your math, it will be fine. So, okay. All right, ready for the next one? Okay. Oh no, more reading. Okay, so the quantity of the chloride in the municipal water supply is determined by titrating the sample with Ag+. The precipitation reaction taking place during the titration is. All right, what is titration? Usually it's neutralizing. In this case, it's precipitating. Titration is just you're doing a reaction in the lab that's quantitative, so that if you don't know the concentration of something, but you do know the concentration of something else, you will be able to figure out the unknown. Okay, and typically it's let's see, let's Google a picture. You may have done it. Did you titrate to a pink with the burettes last year? In Miss Bennett's? Titrate you like this? These used a burette. Right, you drip stuff in and you turned it until it turned pink. Y'all remember doing that? she must have been scared of y'all. All right. Okay, so basically titration usually involves this type of setup. And usually it's an acid and base. In the particular problem we're talking about, it's not. But in this case, there's a solution in the burette that contains the titrant. It's what you're titrating with. And then the flask contains the other solution to be titrated. And it has an indicator in there. And that indicator changes color, usually by pH. So if it's an acid-base titration, that indicator is going to change color when the acid has neutralized the base. Does that make sense? That's kind of the concept behind it. So if you know the concentration of the stuff in the burette, and you know how much you dispense into the known amount of acid in here, you have the exact same problem we just did, right? Like if we did, go back to the last one. If you knew that the HCl was in the beaker, or in the flask underneath, right, and you happened to put in 27.3 milliliters of some acid, some unknown concentration of acid into that flask, and then in the burette you had BaOH2, you knew the concentration of it, and you dripped until it turned pink, and when you did, you dispensed 134.5 milliliters of this, of the BaOH2. You can then solve for the concentration of the acid. That's what you just did. Okay? You just don't like the word titrate and titrant, and right, it starts making it sound like it's something magic. Titrate just means it reacts. Okay? It's just a particular setup. So in this case, this is also how they check the chlorine in the water on the boats. When Jody was in the Navy, he was on submarines. They have seawater that they have to change into fresh water, right? Well, what's in seawater? Salt. It's got the chloride ions and sodium ions. They titrated with silver nitrate to see if there was any chloride in there. And so, because if silver ions get mixed with chloride ions, they make silver chloride, and it's a white solid, so they can see it. So anyway, that's kind of what's going on. All right, the end point of this type of titration is marked by a change in color of a special type of indicator. How many grams of chloride ion are in a sample of water if 20.2 milliliters of 0.1 Ag plus is needed to react with all the chloride ions in the sample? If the sample has a mass of this, then what's the percentage of the chloride ion? Sounds completely different than what you've been doing. But is it? It's not. It's exactly the same problem. It just reads differently. Okay? So write down what you know. You still know a volume of the Ag plus. So it's 20.2 milliliters. You still know a molarity of the Ag plus. You need to know, instead of knowing a volume and wanting to know a molarity, they want to know grams this time. And they want to know grams of the chloride ion. It is still a stoichiometry problem. How do I know it's still a stoichiometry problem? Huh? Right, I changed substances. I went from Ag plus to chloride ions. Okay, so if it's a stoichiometry problem, we have to have a balanced equation. We don't like to write balanced equations with ions, do we? Mass percent. Mass percent. All right, so chloride ions and silver ions. So if silver plus reacts with Cl minus, what is it going to make? Just makes AgCl, and that's the solid. So yeah, we wrote a net ionic, but it's the same thing. So again, it nicely balances as a 1-to-1, so it's kind of easy. So, but we'll write it all out. So the molarity of the Ag plus will equal the moles over the liters. We know the molarity. .0202. So that gives us .00202. Make sure I did my math right. Gives us our moles of Ag plus. Right? Same thing we did last time, is it not? Same thing. So now we have the stoichiometry part. We have to go from moles of Ag plus to moles of Cl minus. And then we have to go from moles to grams. How do we get to grams? Molar mass. So chlorine's 35.5. Does it make any difference that it's an ion? Nope, because what's the only thing that's extra on the chlorine? An electron. And what do we really say? Electrons don't weigh anything. Right. So somebody do the math for us. 717 grams of chloride ions. So that's A. That's the answer to A right there. Oh, 0.07? Okay, so we missed a 0. All right, we'll correct it. 0.07. So is that right now? 071. That's 2 sig figs. So do we keep the 7? 0.071. It is a 7 at the end. Goodness gracious. Poor Jack in this video. Okay, so 0.0717 grams of Cl minus. So that answers A. Then B says if the sample has a mass of 10 grams, what is the percentage of chloride in the sample, basically? So any percentage is a what? A part over a whole, right? So it's going to be percent by mass because that's what they gave you. So any percentage is a part over a whole. What's the part? Right, the part that's chloride. So 0.0717 grams of chloride in the total grams of the substance, whatever it is, sample. We'll just call it sample. Times 100. So 7.1. 7.12. So somebody do the math. Make sure I didn't do the. So times 100 is 7%. Is it 0.7? Okay, then I messed up. All right, so that. Okay, so although it looks completely different, it's still something you know. So don't panic on those when you get them on a test and just because it looks different. is not. I promise.
So
What?
it's not 0.07 after you multiply
Oh.
by 100? No, because it's divided by 10, so you add another zero. It's divided by 10. I had added an extra zero in my calculator.
Okay. So is it right? Is it written right?
Yes.
Okay, good.
Divided by 10 is 0.0717, and then you move the decimal place to 0.7.
Yeah, and I moved it wrong. Okay, so we're good? All right, there's that. All right, one more type, and I didn't type out an example, so let me write one. Let's do another one. Because it was what James was asking about the other day. What if you mixed 100 milliliters of 0.2 molar AgNO3 and 50 milliliters of 0.1 molar NaNO3. And I want to know what's the concentration, so molarity, concentration is molarity, of nitrate ions in the final solution. Mm-hmm.
Does this just make AgNO3 and NaO?
Right. If you look at it, nothing reacts, right? Because if you start looking at it like a chemical equation, you get the same thing on the other side, right? So nothing really reacts. So this is not really a reaction happening. So what's going on? What does happen when they're put in water? They dissolve, but they also dissociate and become ions, right? Both of them split into ions. So the silver nitrate is going to, I should have picked something that had two, but I didn't. Oh well. Want to change it?
Sure.
Let's change it and make this magnesium nitrate so that we have two nitrates from that one. So we'll change this to magnesium. Sorry, all your papers will be. Let's do that. All right, so the magnesium nitrate, when it dissolves, except my little thing's not working. There it goes. When it dissolves in water, we'll make one Mg plus ion, and it'll make two NO3 minus ions, right? That's how it will exist in solution. It'll dissociate into its ions. And the NaNO3 will split into its ions. And we only get one NO3 from there. You agree with that? Right? They'll both dissociate, so those ions will be running around. All right. Can we simply, in other words, can I add molarities? Like if I know the molarity here and I know the molarity here, can I simply add the molarities to get the new molarity? No. Think about Kool-Aid, right? If you had red Kool-Aid that was really, really concentrated, so like let's say it was 10 molar, I don't know, making up stuff, right? If it was 10 molars, really dark red, and you mixed it with something that was 5 molar that was light red, would you get 15 molar? No, that doesn't make any sense, right? Because the dark red and the light red would make something in between, right? So you can't add concentrations, but you can add moles. Okay, so what we have to do is we have to know how many moles of NO3 comes from here. So we have to find the number of moles of NO3 that come from the magnesium nitrate, and then we need to know the number of moles of NO3 that come from the sodium nitrate. And then because nothing reacts, both of those are added together. We can add those, right? And we'll get the total number of moles of NO3 in the solution. Will that solve our problem? Because what do we need? We got to get to concentration. But if we can also add the volumes, right?
But what is the concentration?
Molarity. Concentration is molarity. There are other ways to express concentration, but all we know right now is molarity. We're not going to do the rest of them. So, all right, so all we know is molarity. So concentration for you means molarity. All right, so yes, we can also find the total volume. by adding the two volumes, right? So 100 milliliters plus the 50 milliliters. And yes, you have to assume that the volumes are additive. And it usually on an AP question would say that. All right, so how are we going to find the number of moles from the magnesium nitrate? Yeah, you have the same thing you had in all the rest of the problems. You have a volume, you have the volume, and you have the molarity, right? And then you have a volume and you have a molarity of the other one. All right, so let me write it on the next page because I've got scribble all over that one. So what we know is we have 100 milliliters of 0.2 molar MgNO3, and we had 50 milliliters. What molarity did I put? 0.1? What did I put? 0.1? 0.1 molar NaNO3. Okay, so let's figure out how many, oh, I forgot my 2. All right, so molarity equals moles over liters, and we'll do the MgNO3 first. So 0.2 molar MgNO3 is going to equal, and you certainly can just multiply. You don't have to do this setup. I'm just trying to be consistent so that everybody can follow it. All right, so X equals 0.02 moles of MgNO3 2. Do I need moles of MgNO3 2? I got to get all the way to what? Of the NO3 minus, right? So for every 1 mole of the magnesium nitrate, how many nitrates are coming off? 2. There are 2 moles of NO3 minuses. So we have 0.04 moles of NO3 minuses from the MgNO3 solution. Agree? Got to do the same thing for the sodium. So 0.1 molar of the sodium nitrate equals moles over 0.05 liters. So we multiply 0.005 moles of NaNO3, and for every 1 mole of NaNO3, whoops, how many nitrates do we get? 1 mole of NO3. So this one's 0.005 moles of NaNO3. Now what are we going to do? We're going to add them up, right? So if we add them up, we get 0.045 moles of NO3 minus total. Agree? And then if we have to find the molarity of the NO3 minus, we have to take those moles and divide it by what? That total amount of volume, right, which was 0.15 liters. So 0.3? What? 0.3? 0.3 molar NO3 minus. It's kind of tedious. I'll give you that. It's a little tedious. But conceptually, do you get it? Right? The NO3s come from both places, so you have to add them together. What if you just had to find the new molarity of, let's say they asked for the molarity of the Mg2+.
You only have to do MgNO3.
Right,
Because
you
there's no
just,
MG in the other.
right, you only need it from here. So what number would I put, if I had to do moles over liters, what number would I put on top? The 0.02, right? Because it would be 1 to 1, because I only get 1 magnesium for every one of those. So it would be 0.02 moles of magnesium. What would I put on the bottom?
Still 0.5 because the solutions are still additive even.
Correct.
Both the ions are the same.
Right, right. You still added the 2 volumes together, right? You put one solution in the other. So you could find the molarity of that ion. Okay, so I kind of expect you to be able to find the molarities of any ion in solution. The hard part is finding the molarities of the ions in solution after a reaction, because then it becomes a limiting reagent problem, and yeah, then it becomes really hard. Yeah.
On the
things.
next one, there's like limited reagent molarity problems.
Will there be?
Yeah.
I don't know. There could be.
Will there be on our test though?
I haven't made your test. I
Well,
made about half of it.
Could it be one of these problems and that's just like, the ionic?
Could there be more math and less net ionics? I don't know. Some people might argue the other way. So I'll try to make it half and half.
How do you do number 9 on the
All right, let's do that one then. Number 9 on the review. Might help if I had a review in front of me. Here, I opened that answer key. Let me just pull that and print that. I can read it from there. Oh, did it print? Did that print? Or did I already pick it up? What?
Oh, well, yeah, I mean, that's not. Isn't this just not the first thing? You don't have the volume.
Is that printer printing?
It's sitting there.
What is it? Is it doing? Is it? Oh, maybe it's not plugged in. Maybe that was the problem. Okay, somebody, can I look over your shoulder? All right, the concentration of hydrogen peroxide in solution is determined by titrating, which just means what? Reacting 10 milliliters of the sample of the solution with permanganate ions according to the following equation. If it requires 15.2 milliliters of 0.103 molar permanganate to reach the equivalence point, what does that mean? When they finish reacting. So like neutralizing for an acid base, right? When it finishes reacting, what is the molarity of the hydrogen peroxide solution? So again, it's the exact same problem. Let me write this equation down and then I'll give you this back. All right, so 2 MnO4 minus plus 5 H2O2 plus 6H plus goes to 2 Mn2 plus 5 O2 plus 8 H2O. Next unit you get to balance these, by the way. Electrochem. All right, we know we have 15.2 milliliters of 0.103 molar permanganate, and we know we used a 10 milliliter sample of, we don't know molar, what is it? Oh, hydrogen peroxide. Okay, there you go. Okay, so now that I wrote it like that, does it look exactly the same as the others? Yes. What?
I kind of misread it and I found out what the molarity of water was after it. Anything that hydrogen peroxide was water. Do you by any chance have to put both that way?
Well, because it's not gonna work. Yeah, it's not gonna work. All right, so same thing. We have to know the moles from this. So are we at the point we can now see 0.0152 liters times 0.103 molarity will give me moles of MnO4? Can we see that? All right, so somebody do the math and give me that number.
It's 0.0015656.
Okay, we'll call it 157. Good enough?
157, yeah.
All right, moles of MnO4. And now what do I do next? Convert to hydrogen peroxide, right? Now it's stoichiometry. So 0.00157 moles of the MnO4 minus. How many MnO4 minuses are going to react? 2, right? So 2 moles of MnO4 minus will react with 5 moles of H2O2. All right, somebody do that math. Oh, I didn't hear you. What?
0.00395.
3925. Is that what everybody got? All right, that's moles of H2O2, but they didn't ask us for moles. They asked us for molarity, right? So if we know the moles and we know the liters, we can simply divide the moles by the liters, and we will have molarity. So what's the molarity? 0.3? Did I do the zeros right? Is that right? All right, so my best suggestion, if you're reading problems and don't know where to start, is to do exactly what I did. Write down the information that you know and what you need to know, and maybe it'll jump out at you what you need to do.
Where did you find that the liters for the H2O2? Where
In the,
Okay.
yeah, it said it somewhere in the, yeah, I have two of the same thing now. I have two of the front page and not the back page. Okay. All right, do you think that's enough on the math, or do we need, is there more on that sheet that we need to do? Mm-hmm.
Why wouldn't you go to solve for molarity of water and this is by the equation?
Well, water doesn't really have a molarity because it's a pure liquid.
But it has how many moles are on the equation and overall.
Well, yeah, you could mathematically do it. It's just not. It just doesn't mean anything.
And then number 8 of it, just seeing if I got 0.1 everything pretty much.
Number 8.
I don't know if that's correct.
Oh, apparently the answer key does not have the other pages. So I'll have to do it. Or it's on another page. What's number 8 say?
What are the concentrations of each ion in solution after 50 milliliters of 0.2 molar NaCl is mixed with silver nitrate, and they both have the same molar and liter amount of volume,
Okay, it's this.
and 50 milliliters.
All right, so this is 50 mil. How much was the first one?
50 milliliters.
They were both 50 milliliters of 0.02 of both. And it asked for the constant.
Just 0.2, sorry, just 0.2.
Oh, not 0.02, 0.2.
Yeah, I say 0.2.
Oh, sorry. That's okay. No, I was listening. I don't have the paper in front of me. All right, so, and it asked for the molarity of the chloride ions
Each ion.
of each ion. So that means you got to find it for chlorine, you got to find it for H plus, and you got to find it for Ag plus, because those are the right. Actually, this is solid.
And NO3, AgNO3.
Oh, this is AgNO3. This is a reaction one. Yeah, this is a reaction one. All right, so when HCl reacts with AgNO3, what does it make on the other side? Right. Right. That's a solid. So this is the one, that's basically the problem I was just talking about. And you have to find all the ions of everything in there. Okay, so all of the chloride ions go into the precipitate if it's the limiting reagent, right? Nice that these are 1 to 1 to 1. And these are exactly the same. Why does that make this problem a whole lot easier? Because what? Well, you can find moles easier, but the nice thing is if they're 1 to 1 and they both have the same number of moles, there's no limiting reagent. They both run out at the same time. So you don't have any excess left over. So that makes life nice. So you could, I would probably write it like this at this point. I would put them underneath the thing. Times 0.2. So does this come out 0.1? So 0.1 moles of HCl. Then I'm going to have 0.1 moles of AgNO3 to start with, right? When both those things react, since they're 1 to 1, you're going to use up all of that. Are you not?
Are you doing number 8 on the sheet?
Yes.
Doesn't it say NaCl?
Oh, I don't know. I don't have the sheet in front of me.
Oh, sorry.
It'll work the same way. It says Na. It says Na instead of HCl.
That's correct.
Okay, it doesn't really change anything. Is that right now? Is that what it is? NaCl and AgNO3?
Yes.
Okay, I just heard him wrong. I'm not looking at the paper. All right, so it doesn't change anything.
Yeah, I was just confused on what you were doing.
Yeah, sorry. So anyway, if they're both 0.1 moles and they're 1 to 1, then when I use up all 0.1 moles of this, I use up all 0.1 moles of that. Agree? And so there will be none of these left over. How many moles of the AgCl will I make? I will make 0.1 moles of AgCl. And how many moles of the NaNO3 will I make?
I like that problem.
Yeah. Yeah, it comes out nice. There is no excess, so it makes it nice. The problem now is, okay, what's in solution? NaNO3 is what's in solution. So there are, according to this, if everything reacts, right, there are no Ag or Cl minus in solution because there's no leftover, right? They're in the solid, so they're at the bottom. So there's no ions in solution because they're together as a solid at the bottom of the beaker. The NaNO3 is the only thing left in solution. What's their concentration? If there's 0.1 moles of Na plus and 0.1 moles of of NO3 minus, right? Right? Because there's one, so every time that dissociates, I'm going to get one of those and one of those. So 0.1 moles of Na and 0.1 moles of NO3, what's the new volume? 0.1 liters, right? So the new molarity is 0.001? 01 or 00? Oh, just one. I can't, yeah, it's been a long day. Whoop. Just one. No point anything. It's just one. Just 1 molar Na plus and 1 molar NaNO3. Or just NO3 minus. The problem comes when this isn't even, right? Like, let's say instead of 50 milliliters, I had 100 milliliters. What's that going to do to the whole problem?
Change it.
Change it. Yep, it's going to change it. Yeah, I'm going to have an excess amount of the silver nitrate, right?
So like number 7.
So, so it's like number 7? I don't know. I've got to print the other paper for me.
Yeah.
Right. So then this, in that case, this is excess. And so you're going to use up all, so there won't be any chloride ions in solution, but there will be some silver because there's going to be leftover from here. And that's going to make it a little tricky mathematically. So, let me see your paper. Right, right, right. This to Ag, but you have to subtract out how much gets used up. You have to find out the leftover. Right. No, number 7 is not this. Why is number 7 not this? Nothing happens in number 7. Number 7, there's no reaction. It's more like this one. Right, where the NO3s, nothing, you just combine them. Because there's no really reaction.
And if there was excess AgNO3, there would also be more NO3 in the solution, right?
Yes. Yes. Do you want me to do it with those numbers?
Yeah.
All right, so let me flip the page and do it again then. We had 0.2 molar NaCl, and we said it was 50 milliliters, and then we had 0.2 molar AgNO3, and we said we had 100 milliliters this time, right? So in this case, I think it's easier to see if I write the little reaction out. Who's crunching on candy? I don't care, I just heard it. All right, so the 0.05 times the 0.2 still gives us the 0.1 moles of NaCl. This time we have 0.2 times 0.1, so we get 0.2. I missed the 0, didn't I? Yeah, this is 0.01, and this is 0.02 moles. We agree? All right, instead of doing all that stoichiometry stuff for limiting reagent, once I'm in moles, to me it's easier just to do it straight down the line kind of here. So which one of those two is limiting reagent? The NaCl, because they're 1 to 1, right? And I only have 0.01 of that, and I have 0.02 of this. So I have plenty of silver nitrate. So this is my limiting reagent. This is my excess reagent. So assuming that the reaction goes to completion, we will use up all of the NaCl, right? How much AgNO3 will we use up? The same amount. So 0.01 moles of that will get used up. How much silver chloride will we make? Same amount, right? Because they're 1 to 1. So 0.01 moles of this get made. So I put a plus sign in front of it. And 0.01 moles of the NaNO3 get made. So how much do we have? I could have drawn a straight line, sorry. So there's none of that left. There's 0.01 moles of AgNO3 left. There's 0.01 moles of AgCl sitting at the bottom. And there's 0.01 moles of NaNO3. Which ones of those still have ions in solution? Yeah, this one and that one, right? So now this kind of looks like the other problem, right? This is a solid, so this is sitting at the bottom. Agree? So we don't really care about that because they asked us what the molarity of the ions were, right? That was kind of the question. So the only things in solution that are dissociated into ions are this silver nitrate and this sodium nitrate, right? All right, so what's the molarity of the silver ion? How many moles of silver Ag plus do you have in solution? 0.01, because it's 1 to 1, right? For every one of those, I'm going to get 1 Ag plus. You want me to write it out so you see it? Oh, that's a 3. You get 1 mole of Ag plus. So you have 0.01 moles of Ag plus in solution. What's the new volume? 150. So divide it by 0.15 liters, and you will have the molarity of the Ag plus. Somebody want to give me that number? 0.06? Okay, we'll call it 0.067. All right, then the molarity of, let's do the Na. So we don't, because right, the NO3 shows up in both places, agree? So we're going to have to add. So let's skip over and do the Na, and then we'll come back and do the NO3. So we have 0.01 moles of NaNO3. Again, it's 1 to 1. I don't care if you write this step, I'm just writing it so that you don't think I magically made up a number. And it'll be divided by the same volume, so 0.067 of Na plus. We agree? Okay, the nitrates are the only problem because we have some here and we have some there, right? Okay, so the molarity of the NO3 minus, we have 0.01 moles from the AgNO3, and we have 0.01 moles from the NaNO3, right? So we have a total of 0.02 moles of NO3 minus. And we can divide that by the 0.15 and 0.12-ish. 134. Oh, I didn't put molarity. I didn't put my capital M. So there's the concentration of all the ions in solution. And why is the chloride not there?
Solid.
Because it's a solid, and it was in the limiting reagent, and it's in the solid. So there's no more chloride ions in solution. Yeah, the sodium didn't get used up and didn't rewrite. So the sodium concentration is the same. Well, not the concentration, but the moles are the same as it started, right?
So basically, the silver in the precipitate does not count as ions because it's solid at the bottom. But chloride was all used up, so there's no ions left.
Right.
The silver was in
Yep. That's exactly right. Exactly right. That's hard. I mean, I think that's hard. That's hard to conceptually, because I write out all the math and you're following the math, but you're missing the big picture when you follow the details sometimes. And so really, exactly what Jack just did was summarize it. Is there's no chloride ions because all of them got used up in the solid, so they're all sitting at the bottom. But because all the silver did not get used up because it was an excess reactant, there's still some silver ions floating around in solution. So we have to have that concentration, and that's just what's left, right? How many moles of Ag plus did you start out with? 0.02. But the other 0.01 of them sitting in here, right? Okay, so if you get it conceptually, you're doing well. You're doing well. You'll get it. Does it make sense?
If you put one of these test, I'll make them either do it myself.
We're doing
Make it a multiple
Why not?
choice.
Can you make it one I can pick? Jack.
James.
Jack, it's the J class. Sorry.
If Ag was like lithium and the AgCl didn't make a reaction, then the Na would have the same molarity as the other, and nitrate would have the same molarity as Ag because Ag didn't get used up at all.
Say that again. If what was lithium?
Ag because Ag wouldn't form anything with Cl, but it still has a +1 charge.
Well, if nothing formed, if no solid formed,
But,
then
like,
it's
just theoretically, like
it's
not, like
they're
just
all
for the
ions.
number portion, like from like 100 milliliters in 0.2 m, like it would 0.134 molarity would be that of the lithium.
I'm not following.
No.
Write it out. Write it down, and I'll look at it. All right, is that enough of the math? You ready to go over the net ionic stuff? Yes. You want to see if you got that right? No. Hopefully. Maybe. Or is there any of the multiple choice on there that you wanted to do? I have got to find that sheet. Let me just stop that video. It's gonna have to be enough. Where's this there?